When was the last time NASA went months without bragging about images from the James Webb Space Telescope? When has Hubble ever captured something extraordinary and then just stopped talking about it? That's the unsettling reality surrounding 3I Atlas, our third confirmed interstellar visitor. Atlas arrived in July with characteristics that raised a lot more questions than they answered. For the first weeks, we received regular updates and stunning imagery. Then something changed in August. Hubble went silent. Webb's spectroscopy vanished into analytical limbo, and we've only gotten generic, ultra-rationalized updates from NASA. Even as Atlas approaches its closest encounter with Mars, the institutions we trust to show us cosmic wonders have retreated behind a wall of silence. This begs the question, what is really happening behind the curtains, and what have they discovered that they're not telling us? On tonight's exploration, we dive into the chilling theories behind the lack of new images, and the most terrifying possibility no one is talking about. Part 1. The missing images. Something is wrong behind the scenes. As of September 22nd, the most recent public releases from our flagship telescopes paint a troubling timeline. Hubble's last image of 3I Atlas was captured on July 21st, posted to the world on August 7th. The James Webb Space Telescope observed the object on August 6th, releasing only spectroscopy notes. A single image from Gemini South broke the silence, released September 4th and 5th, but even this was taken on August 27th. Think about that for a moment. Our most powerful eyes in space have gone nearly silent on the most interesting object to visit our solar system in years. The official NASA page for 3I Atlas offers a convenient explanation. Visibility would drop after September as the comet draws too close to the Sun from Earth's line of sight. Solar conjunction makes observation difficult. It's a perfectly reasonable, scientifically sound explanation that should put our minds at ease. But does it really explain the drought of imagery we've been experiencing? Let me paint you a timeline that should disturb anyone who's been following space exploration. July 21st. Hubble captures what becomes its final public image of Atlas. August 6th. Webb observes the object but releases only technical spectroscopy data. Late August, Gemini South manages to capture imagery that won't be released until early September. September 22nd. The public is still waiting for new flagship telescope images. Nearly 2 months of relative silence from the instruments we depend on to show us the wonders of the cosmos. The terrifying theory that's been circulating in certain circles suggests this silence isn't accidental. What if something too strange, too unprecedented, too difficult to explain has been captured in those missing weeks? What if the images exist, but they're being held back because they challenge everything we thought we knew about? Comets, about interstellar visitors, about what's possible in the dark spaces between stars. But let's be fair to the mundane explanations. Telescope time is precious, scheduled months in advance. Analysis pipelines for major observatories move slowly, carefully. Scientists prefer to understand what they're seeing before they share it with the world. The geometry of space is unforgiving. Sometimes objects simply become impossible to observe from Earth's perspective. These are the rational reasons for any gap in coverage. Yet the reports we do have from mid-September describe something extraordinary, faster than predicted, brightening multiple magnitudes beyond what the models suggested. Now, these claims come from amateur observers, and their estimates haven't been confirmed in peer-reviewed releases. The factor of 20 times brighter than expected could be observer error, instrument differences, or measurement inconsistencies. But what if it isn't? The Mars flyby approaches on October 3rd, just days away. If space agencies have new data, if they've captured something remarkable or disturbing in those missing weeks, the clock is ticking. Mars represents our best chance for close-up observation, for ground truth that could either confirm or shatter the theories swirling around this mysterious visitor. You deserve to weigh the real science against the scary speculation. You deserve to see all the evidence, both the reassuring and the unsettling, and make your own determination about what we might be witnessing. The question isn't whether scientists are hiding something, it's whether the silence itself has become more revealing than any image could be. We've seen how previous interstellar visitors were handled. Oumuamua dominated headlines with constant updates. Borisov became a media darling with steady streams of images and data. Atlas feels different. The coverage has been more cautious, more measured, more careful. Why? Soon, Mars orbiters may break this drought with close-range observations that could change everything. The question is whether those images, when they come, will be shared with the same transparency we've come to expect, or whether the pattern of selective silence will continue, leaving us to wonder what wonders or horrors are being filtered from our view of the cosmos. Part 2. What we know so far. 3I Atlas emerged from the cosmic dark on July 1st, 2025, spotted by the Atlas survey system that gives it its name. The third confirmed interstellar visitor to grace our solar system, following the mysterious Oumuamua and the more conventional Borisov. But Atlas has proven to be something else entirely, a cosmic riddle wrapped in a coma of frozen gases. The trajectory brings it uncomfortably close to Mars on October 3rd, 2025. Closest approach, approximately 30 million kilometers, or roughly 19 to 20 hundredths of an astronomical unit. The European Space Agency has confirmed their Mars orbiters will attempt observations during this encounter. Mars Express, ExoMars Trace Gas Orbiter, possibly even NASA's Mars Reconnaissance Orbiter if the geometry allows. This represents our best, perhaps our only, chance to capture high-resolution imagery of Atlas before it continues its journey toward the Sun. Perihelion, the closest approach to our star, arrives in late October. October 29th to 30th, at approximately 1.36 to 1.4 astronomical units, just inside Mars's orbital distance. This is where comets traditionally put on their greatest show, where the sun's heat drives spectacular outgassing events that create the tales we associate with these cosmic wanderers. But Atlas has already been defying expectations. For Earth's safety, NASA has been clear. This object poses no threat to our planet. Its closest approach to Earth comes in December, at roughly 1.8 astronomical units, farther than the Sun. We are spectators to this cosmic drama, not participants in any collision scenario. But what makes Atlas truly extraordinary lies in its composition and behavior. The SphereX mission detected something unprecedented, a carbon dioxide coma extending outward for approximately 348,000 kilometers. To put that in perspective, this gaseous envelope stretches for half the radius of our Sun. No comet in recorded history has displayed a CO2 coma of this immense scale. The morphology, the shape and structure of Atlas defies conventional comet behavior. Hubble images and ground-based photography reveal a sun-facing plume, an anti-tail that points directly toward our star rather than away from it. This contradicts the basic physics we teach about solar wind pressure and radiation effects on comet tails. Something about Atlas's dust grain sizes, its rotation, or its internal structure is creating patterns we don't understand. Reports began surfacing in late August and early September of a color change. Observers noted a green tint developing in Atlas's coma, likely caused by dicarbon or cyanide compounds energized by solar radiation. But here's where the mystery deepens. This green coloration hasn't been firmly confirmed through spectroscopic analysis. We're relying on visual observations, photographic evidence, and educated guesses about chemistry that may or may not match reality. The brightness trend has become perhaps the most unsettling aspect of Atlas's behavior. Earth Sky and other astronomy outlets have compiled reports from observers noting faster than predicted, brightening as the object moved inside, approximately 2 astronomical units from the Sun. The numbers vary dramatically depending on aperture sizes, filters used, and observing conditions. This uncertainty isn't unusual. Amateur astronomy often produces scattered data points that require careful statistical analysis to interpret. But the discord in brightness measurements reveals a deeper issue. Many of our most recent images come from amateur astronomers stacking multiple exposures to reveal faint details. The flagship telescopes that should be providing definitive measurements have been notably quiet. Their pipelines move slowly, especially when objects are approaching solar conjunction, where observing becomes technically challenging. The release schedule creates a perfect storm of uncertainty. While amateur astronomers share their latest captures on social media within hours of observation, Professional telescopes may hold data for weeks or months during analysis and peer review processes. This gap between citizen science and institutional astronomy has never felt more pronounced than with ATLAS. European Space Agency scientists have indicated that spectroscopic data from the James Webb Space Telescope's August 6th observations is still under analysis. What are they finding in those spectral lines? What chemical signatures are proving so complex that they require extended study before publication? The silence around these results feeds speculation that something unexpected, perhaps unprecedented, has been discovered. The trajectory of ATLAS aligns closely with the ecliptic plane, the disk-like region where planets orbit our Sun. This positioning enables the close Mars encounter and sets up a future Jupiter flyby in 2026. Such precise alignment with our solar system's architecture strikes some observers as more than coincidental, though orbital mechanics can produce surprising geometries through natural processes. As we stand on the threshold of the Mars flyby, the accumulated mysteries of ATLAS create an atmosphere of anticipation mixed with unease. The missing images from our most capable telescopes, the unprecedented scale of its carbon dioxide coma, the bizarre anti-tail behavior, the uncertain brightness evolution. Each piece of evidence, taken alone, might represent interesting but explicable comet science. Together, they form a pattern that challenges our understanding of what interstellar visitors should look like. Part 3. Why the silence matters. Memory plays tricks on us, especially when we're accustomed to a steady diet of space imagery. Think back to Comet Neowise in 2020, when social media flooded with nightly photographs of its spectacular tail arcing across Earth's skies. Remember the Bennu asteroid sample return, documented in real time through hundreds of images as OSIRIS-REx approached, touched, and departed its target. Space exploration has conditioned us to expect visual documentation of every major cosmic event. ATLAS feels different. The public releases from Hubble and Webb have been sparse, measured, carefully curated. Since August, the flagship observatories have maintained what can only be described as a visual fast. This isn't entirely unprecedented. Telescope time is precious, and not every observation becomes a press release. But for an interstellar visitor of ATLAS's apparent significance, the silence is deafening. NASA's own documentation explicitly acknowledges a visibility gap after September due to the sun's glare. Solar conjunction makes observation from Earth challenging or impossible for certain periods. This sets reasonable expectations for any data drought. But it also creates something more dangerous, an information vacuum that conspiracy theories rush to fill. Human psychology abhors uncertainty. When official channels go quiet during periods of peak interest, alternative explanations multiply in online forums and social media echo chambers. The absence of new Hubble images becomes evidence of a cover-up. The delay in Webb spectroscopy results transforms into proof that something too strange for public consumption has been discovered. Rational explanations for observational gaps lose the battle against more sensational possibilities. The European Space Agency and other international partners did release the Gemini South image captured on August 27th, shared with the public in early September. This proves the astronomical community isn't maintaining complete silence about ATLAS, but the public has been trained to expect the regular cadence of Hubble portraits and Webb infrared revelations. When those sources go quiet, even briefly, it feels like abandonment. Media coverage patterns reveal another dimension of the silence. While ATLAS coverage peaked in July and August, September brought a noticeable shift in focus toward other celestial objects. Comet Lemon's rising brightness captured headlines. The fragmentation of Comet Swan provided dramatic imagery. To observers tracking ATLAS specifically, this diversified coverage might feel like intentional distraction, though it more likely reflects the natural ebb and flow of astronomical news cycles. The psychology of conspiracy thinking thrives on perceived patterns. When multiple unusual events occur simultaneously, unusual comet behavior, reduced telescope coverage, media attention shifting elsewhere, pattern-seeking minds connect dots that may not actually be connected. The timing of ATLAS's conjunction period unfortunately coincides with maximum public interest in its Mars flyby and perihelion passage. Data analysis pipelines at major observatories prioritize accuracy over speed. Unlike amateur astronomers who can share images within hours of capture, institutional astronomy requires peer review, calibration checks, and careful interpretation before public release. This necessary caution protects scientific credibility, but creates gaps that speculation rushes to fill. Public trust in scientific institutions has become more fragile in recent years. From climate change debates to pandemic response controversies, the relationship between expertise and public understanding has grown more complex. When space agencies maintain silence during periods of high interest, even for legitimate technical reasons, it activates existing skepticism about official narratives. The question isn't whether NASA, ESA, or other agencies are hiding something dramatic about Atlas. The question is whether the perception of secrecy has become more damaging than any actual classified information could be. In the social media age, absence of evidence becomes evidence of absence, or worse, evidence of intentional concealment. What the public wants now is simple: new images as Atlas approaches its Mars encounter and subsequent perihelion passage. High-resolution photography that shows the object's current state, its evolving coma structure, and any changes in its unusual anti-tail behavior. The appetite for visual confirmation of Atlas's strangeness has only grown during the weeks of relative silence. What scientists want is more complex, detailed spectroscopic analysis to confirm the chemical composition of that massive carbon dioxide coma, precise measurements of the nucleus size and rotation period, understanding of the physical processes creating the sun-facing plume. These goals require time, careful analysis, and often multiple observational campaigns to achieve confidence in the results. The disconnect between public hunger for immediate imagery and scientific need for thorough analysis creates the perfect conditions for conspiracy theories to flourish. Every day without new official images becomes another data point in arguments that something is being deliberately withheld from public view. Soon, Mars orbiters may provide the breakthrough imagery that could either satisfy public curiosity or deepen the mystery further. The question that haunts this entire situation is whether those images, when they arrive, will be released with the transparency the public expects, or whether new reasons for caution and delay will emerge, extending the silence that has already lasted too long. Part 4. Theories behind the silence. Let's examine the possible explanations for Atlas's missing imagery with the cold. The logic of elimination. Start with the mundane reasons, the technical realities that govern how our most sophisticated instruments observe the cosmos. Solar elongation presents the most straightforward constraint. As Atlas approaches conjunction with the Sun from Earth's perspective, the observing geometry becomes increasingly challenging. Telescopes can't point close to the Sun without risking damage to sensitive instruments. The Hubble Space Telescope, for instance, maintains strict pointing restrictions to protect its cameras and spectrographs from solar radiation. This creates observational dead zones where even the most interesting targets become temporarily inaccessible. Q time represents another harsh reality of modern astronomy. Hubble and Webb operate on observation schedules planned months or even years in advance. Target of opportunity requests exist for truly extraordinary events, but these interrupt carefully planned science programs. The threshold for disrupting established schedules is high, requiring compelling scientific justification beyond mere public interest. Atlas, while unusual, may not have met the criteria for emergency observation time. Analysis lag affects every major astronomical discovery. Professional telescopes produce data that requires extensive processing, calibration, and interpretation before it's suitable for public release. Unlike amateur astronomers who can share raw images hours after capture, institutional astronomy demands peer review and quality control. The James Webb Space Telescope's August 6th spectroscopic observations of Atlas are likely still working through these analysis pipelines, with scientists carefully interpreting each spectral line before drawing conclusions. Operational trade-offs further complicate the situation. Webb's near-infrared spectrograph data from August 6th represents just one piece of a larger observational puzzle. Not every scientific observation produces a press-worthy image. Spectroscopy reveals chemical composition, but doesn't necessarily create the visually striking pictures the public craves. The gap between scientific data collection and public imagery release can span weeks or months. But let's venture into more speculative territory, clearly labelled as such, because these theories have gained traction in online communities tracking Atlas's behaviour. The panic prevention hypothesis suggests that space agencies might delay releasing visuals if they appear too anomalous, too difficult to explain, without causing public alarm. Imagine if Atlas's anti-tail behaviour had evolved into something that looked artificial or structured in ways that defy explanation. Would NASA rush to share such imagery without first developing frameworks to help the public interpret what they're seeing? This theory assumes a paternalistic approach to information management, where experts filter cosmic revelations to prevent misunderstanding or fear. National security considerations add another layer of complexity. Military surveillance systems undoubtedly track bright objects like Atlas, potentially with higher resolution and better temporal coverage than civilian telescopes provide. But military data rarely enters the public domain, even for scientifically interesting targets. The gap between classified observational capabilities and public information sharing creates space for speculation about what enhanced imagery might reveal. Narrative control during conjunction periods offers a more cynical explanation. If agencies anticipated that Atlas's solar approach would generate observational difficulties and public impatience, they might have chosen to wait it out rather than repeatedly explaining technical constraints. Better to maintain silence until post-conjunction observations resume than to constantly defend the lack of new imagery during difficult observing periods. The counterpoint to all speculation remains visible in the astronomical record. NOAA Lab and Gemini Observatory did share their August 27th imagery in early September, demonstrating that complete suppression of Atlas information isn't occurring. Professional astronomers continue to discuss the object at conferences and in papers submitted to journals. The scientific process continues, even if public imagery has become scarce. Equipment prioritization may explain some of the observational gaps. As Atlas approaches conjunction, telescope operators might reasonably decide to focus limited, observing time on targets that remain easily accessible rather than struggling with increasingly difficult solar elongations. This represents sound operational planning rather than deliberate concealment. International coordination complexities could also contribute to delayed releases. Multiple space agencies and research institutions are studying Atlas independently, coordinating public releases across different organizations, each with their own peer review processes and public relations protocols, naturally introduces delays compared to single-source announcements. The bottom line emerges clearly from this analysis. The silence around Atlas likely stems from logistical and operational constraints rather than deliberate secrecy, but the suspension of regular visual updates during a period of maximum public interest inevitably invites fear-driven theories to flourish. The gap between reasonable explanations and public perception has become as interesting as Atlas itself. The pattern of selective disclosure in other contexts, from UAP reports to pandemic response, has primed the public to expect information management rather than complete transparency. Whether justified or not, this expectation shapes how people interpret gaps in official communication about extraordinary events. As we prepare for the Mars flyby observations, the accumulated weeks of relative silence have created an atmosphere where any new imagery will be scrutinized, not just for what it shows, but for what it might have been edited to hide. The perception of secrecy, whether real or imagined, has become part of the Atlas story itself. Part 5. Governments and Space Control. The machinery of space communication operates through carefully orchestrated channels that few outside the astronomical community fully understand. NASA maintains a public mission mandate, but the timing and framing of press releases undergo curation designed to maximize scientific accuracy while maintaining public interest. The European Space Agency follows similar protocols, balancing transparency with the need for peer review and proper context. This system works well for routine discoveries but creates friction during periods of intense public curiosity about anomalous objects. Classified sensors present a more opaque layer of the observation ecosystem. Department of Defense tracking systems monitor space for threats and debris, capabilities that certainly extend to bright objects like comets and asteroids. These military assets often possess superior resolution and temporal coverage compared to civilian telescopes, but their data rarely enters public channels. The gap between classified observational capabilities and public information creates fertile ground for speculation about enhanced imagery that might exist but remains hidden. The parallel to recent UAP transparency debates becomes unavoidable. Government acknowledgement of unidentified aerial phenomena has followed a pattern of gradual, carefully managed disclosure rather than immediate transparency. This precedent shapes public expectations for how extraordinary space events might be handled. If military pilots' encounters with unexplained objects require years of bureaucratic processing before acknowledgement, what timeline might govern the release of anomalous comet observations? Media focus has demonstrably shifted away from Atlas during September, though whether this represents natural news cycles or more coordinated editorial decisions remains unclear. Headlines have increasingly featured other comets: Lemon's brightening trajectory, Swan's dramatic fragmentation, while Atlas coverage has diminished despite its approaching Mars encounter. To observers specifically tracking interstellar visitor news, this pattern might feel like intentional distraction, though it more likely reflects the media's appetite for visually dramatic, easily explained phenomena over complex scientific mysteries. Comet Lemon's rise to prominence illustrates this dynamic perfectly. Its predicted brightness curve suggests naked-eye visibility by late October, making it accessible to amateur astronomers worldwide. News outlets naturally gravitate toward objects their readers can personally observe rather than telescopic targets requiring specialized equipment to see. Atlas, despite its scientific significance, remains invisible to casual stargazers, limiting its sustained media appeal. The fragmentation of Comet Swan in September provided exactly the kind of dramatic visual content that space journalism thrives on. Breaking apart in real time, creating photogenic debris fields and evolving tail structures, Swan delivered immediately comprehensible spectacle. Atlas's mysteries, its carbon dioxide coma scale, its anti-tail behavior, its unusual brightness evolution, require more technical explanation to convey their significance. Risk assessment in science communication has grown more complex in recent years. Institutions have learned painful lessons about how preliminary findings can be misinterpreted, how uncertainty gets lost in translation from scientific papers to news headlines. The cautious approach to Atlas communications might reflect this learned wariness rather than specific concerns about the object itself. International cooperation in space science creates additional coordination challenges. European, American, and other national space programs must balance their individual, institutional interests with collaborative scientific goals. Timing public releases to avoid conflicts between different agencies' announcement schedules naturally introduces delays that can appear suspicious to outside observers. The question of data sharing protocols becomes particularly relevant for objects like Atlas that cross multiple institutional boundaries. Which organization has primary responsibility for public communication about an interstellar visitor? How do they coordinate with other observing teams to ensure consistent messaging? These procedural questions have real impacts on the flow of information to the public. Public expectations for space transparency have been shaped by decades of dramatic imagery from missions like Voyager, Cassini, and the Mars rovers. The constant stream of pictures from these missions created an assumption that all significant space events should generate similar visual documentation. When that expectation isn't met, even for legitimate technical reasons, it creates cognitive dissonance that conspiracy theories exploit. The selective disclosure patterns visible in other government communications inevitably influence how people interpret gaps in space agency announcements. Whether the topic is national security, public health, or economic policy, institutions regularly demonstrate that information management takes precedence over complete transparency. This established pattern primes the public to suspect similar filtering in space-related communications. Control mechanisms in scientific publication add another layer of delayed disclosure. Professional astronomy operates through peer review processes that can span months from initial submission to published results. Even when scientists have dramatic findings about Atlas, the publication timeline ensures that preliminary results remain within professional circles, while the broader public waits for official announcements. The intersection of scientific caution and public Curiosity creates an inherent tension in how extraordinary discoveries are communicated. Scientists want to understand anomalies thoroughly before making claims that might later require embarrassing corrections. The public wants immediate access to any evidence of cosmic strangeness. Reconciling these different timelines requires skill and transparency that institutions don't always demonstrate effectively. As we approach the Mars flyby window, the accumulated pattern of careful information management around Atlas has created an atmosphere where any new releases will be scrutinized for what they exclude as much as what they reveal. The perception of control, whether justified by scientific caution or driven by other considerations, has become part of the story that future transparency will struggle to overcome. Part 6. Oumuamua's Image. History. October 19, 2017. Pan-STARRS 1 telescope in Hawaii detects something impossible. An object moving through our solar system on a hyperbolic trajectory, clearly originating from interstellar space. Within hours, the astronomical community mobilized with unprecedented coordination. Follow-up observations from telescopes around the globe confirmed what would become the most studied single object in modern astronomy. Oumuamua, our first confirmed interstellar visitor. The transparency surrounding Oumuamua's discovery and investigation stands in stark contrast to the current Atlas situation. Data flowed freely between institutions. Light curve measurements appeared in preprint servers within days. Shape reconstructions, rotation period analyses, and trajectory refinements were shared openly as they developed. The scientific process played out in real time, visible to anyone willing to follow the technical literature. What made Oumuamua's coverage possible was also what made it scientifically puzzling. The object showed no signs of cometary activity, no coma, no tail, no outgassing that would complicate photometric measurements or obscure surface features. This absence of cometary behavior simplified the observational challenge, while simultaneously deepening the mystery of its composition and origin. The famous non-gravitational acceleration detected in Oumuamua's trajectory sparked intense debate, but that debate occurred publicly. Competing hypotheses appeared in journals and were discussed in conferences broadcast to the public. The hydrogen iceberg theory, the solar sail speculation, the nitrogen ice chunk proposal. Each explanation generated follow-up observations and analysis that were shared openly, allowing the scientific community and interested public to follow the investigation in real time. Spitzer Space Telescope constraints provided crucial data about Oumuamua's thermal emission, effectively ruling out certain composition models. These null results were published promptly, demonstrating how negative findings can be as scientifically valuable as positive detections. The transparent handling of Spitzer's non-detection contrasts with the current silence around Webb's spectroscopic observations of Atlas. Light curve analysis revealed Oumuamua's extreme elongation, suggesting a shape unlike any known asteroid or comet. These findings appeared in multiple papers from different observing teams, creating a robust dataset that supported confident conclusions about the object's unusual geometry. The redundancy of independent observations provided cross-validation that strengthened public confidence in the scientific process. The lesson from Oumuamua's coverage appears clear. When anomalies generate immediate public discussion, the accumulation of evidence and competing explanations actually tends to cool rather than inflame speculation. Transparency breeds understanding, while information gaps breed conspiracy theories. The real-time scientific debate around Oumuamua demonstrated how open investigation can handle even the most unusual discoveries. But Oumuamua's lack of cometary activity made it fundamentally different from Atlas. No coma meant no complications from dust and gas that could obscure or confuse observations. No outgassing meant no pressure effects that could alter the object's trajectory in unpredictable ways. The observational challenges were simpler, making rapid analysis and publication more feasible. The international collaboration on Oumuamua research showcased astronomy at its best. Teams from multiple countries shared data freely, building complementary analyses that strengthened overall understanding. This cooperative approach maximized the scientific return from limited observing opportunities while maintaining public engagement throughout the investigation process. Contrast this with Atlas's post-August timeline, where major observatories have been notably quiet despite the object's far more dramatic cometary behavior. The difference in communication patterns raises questions about whether the complexity of Atlas's characteristics requires more cautious analysis, or whether other factors are influencing the pace of public disclosure. Oumuamua's trajectory took it rapidly away from the inner solar system, creating urgency that forced quick decisions about observing priorities and rapid publication of results. Atlas's more leisurely approach to perihelion might remove some of this urgency pressure, allowing more deliberate analysis timelines that nonetheless frustrate public curiosity. The media coverage of Oumuamua demonstrated both the benefits and risks of transparent science communication. While most coverage accurately conveyed the scientific uncertainty and competing hypotheses, some outlets sensationalized the more speculative explanations. This mixed reception might influence how institutions approach communication about equally anomalous objects like Atlas. Professional astronomy learned important lessons from the Oumuamua experience about managing public expectations during the investigation of unusual objects. The balance between sharing exciting discoveries promptly and avoiding premature conclusions requires careful navigation. Perhaps the more cautious approach to Atlas reflects this learned experience. The timing of Oumuamua's discovery in October allowed extensive observations during good viewing conditions before the object became too faint and distant to study effectively. Atlas's discovery in July and its approach to solar conjunction in September created a more compressed and challenging observational timeline that might naturally lead to different communication strategies. Yet the fundamental question remains: why has the scientific openness that characterized Oumuamua research not extended to Atlas investigation? The object displays far more dramatic and easily observable phenomena than its predecessor, yet public information about its current state has become scarcer rather than more abundant. The contrast suggests that either technical challenges or policy decisions are shaping a more restrictive approach to sharing Atlas observations with the public. Part 7. Borisov's Open Book. August 30th, 2019. Gennady Borisov, an amateur astronomer in Crimea, spots something unusual through his homemade telescope. Within weeks, professional observatories around the world confirm his discovery as 2I divided by Borisov, the second interstellar visitor to our solar system. Unlike the enigmatic Oumuamua, Borisov behaved exactly as astronomers expected an interstellar comet should behave, and that conventional behavior made everyone feel comfortable sharing everything they learned. The transparency surrounding Borisov's investigation felt routine precisely because the object conformed to established comet science. It developed a classic tail as it approached the Sun. Its coma evolved predictably with solar heating. Spectroscopic observations revealed familiar water vapor and other volatiles, outgassing in expected patterns. Scientists understood what they were seeing, which made them confident about sharing their observations with the public. Hubble Space Telescope images of Borisov appeared regularly throughout its passage through the inner solar system. These pictures showed textbook cometary behavior, a condensed nucleus surrounded by an expanding coma of dust and gas, with a tail extending anti-sunward under pressure from solar radiation. The visual documentation felt comfortable, familiar, educational. Parents could show these images to children and explain what they were seeing without confronting confusing anomalies. The European Southern Observatory, NASA, and other institutions produced a steady stream of press releases about Borisov's evolving characteristics, size estimates for the nucleus, chemical composition of the outgassing materials, trajectory refinements as gravitational perturbations became measurable. Each update fit neatly into existing frameworks for understanding cometary behavior. Spectroscopic analysis revealed that Borisov's composition closely matched comets from our own solar system's Oort cloud. Water, carbon monoxide, dust particles, all familiar constituents that validated theories about planetary formation in other star systems. The chemical similarity between interstellar and local comets became a compelling scientific story that required no caveats or careful explanations about unprecedented phenomena. When Borisov began showing signs of fragmentation in late 2019 and early 2020, even this dramatic development followed well-understood physics. comets break apart under thermal and tidal stresses. The process, while spectacular, posed no interpretive challenges that might warrant delayed publication or cautious analysis. The fragments behaved predictably, creating photogenic debris fields that made excellent educational content. The key difference between Borisov and Atlas becomes obvious through this comparison. Routine comets generate routine public relations strategies, while anomalous objects create analytical bottlenecks that slow information flow. When scientists understand what they're observing, they feel comfortable sharing those observations immediately. When confronted with behavior that challenges existing models, institutional caution naturally increases. Professional astronomy has established protocols for handling unusual discoveries that require more extensive analysis before publication. Peer review processes, which operate smoothly for conventional results, can become lengthy when reviewers struggle to evaluate claims that push beyond established knowledge. The more anomalous the observation, the higher the bar for publication, and the longer the delay before public communication. Borisov's conventional behavior also made it easier for multiple independent teams to obtain similar results, building confidence through redundancy. When several observatories measure consistent outgassing rates, nuclear sizes, and chemical compositions, the scientific community feels confident about sharing preliminary findings. Atlas's unique characteristics make independent verification more challenging and increase uncertainty about interpretation. The media coverage of Borisov reflected this scientific comfort level. Press releases emphasized the educational value of watching an interstellar visitor behave like local comets, validating our understanding of planetary formation processes across different stellar systems. Journalists could write about Borisov without needing to navigate complex technical caveats or acknowledge fundamental uncertainties about what they were describing. Public engagement around Borisov felt satisfying because the object reinforced rather than challenged astronomical knowledge. Citizens could learn about comet science through following an interstellar example that demonstrated universal physical laws operating beyond our solar system. The narrative was clean, educational, and ultimately reassuring about our understanding of cosmic processes. Amateur astronomers could participate meaningfully in Borisov observations because the object's behavior fell within familiar parameters. Backyard telescopes could capture its tail development, track its brightening curve, and contribute to the overall dataset in ways that professional astronomers welcomed. This broad participation created a sense of shared discovery that enhanced public engagement. The contrast with Atlas's coverage pattern becomes stark through this historical comparison. Where Borisov generated regular updates and educational content, Atlas has prompted careful silences and analytical delays. The difference isn't necessarily sinister, it more likely reflects the challenge of communicating about phenomena that don't fit established categories. Consider the burden placed on institutions when faced with truly anomalous observations. How do you explain a carbon dioxide coma that extends for half the sun's radius? How do you contextualize anti-tail behavior that violates basic expectations about solar-wind interactions? The complexity of explaining Atlas's characteristics far exceeds the straightforward educational opportunities that Borisov provided. The lesson from Borisov's open-book treatment suggests that transparency in space science correlates strongly with comprehensibility. When discoveries fit existing frameworks, institutions feel comfortable with rapid, extensive public communication. When observations challenge fundamental assumptions, the same institutions default to caution, analysis, and delayed disclosure patterns that inevitably generate suspicion about what might be hidden. This pattern raises uncomfortable questions about whether the public receives complete information only when that information reinforces rather than challenges established scientific understanding. Are we seeing the results of natural scientific caution or evidence of institutional bias toward comfortable rather than revolutionary discoveries? Part 8. How Atlas breaks the pattern. The scale of Atlas's carbon dioxide coma defies every precedent in cometary astronomy. 348,000 kilometers of CO. 2 envelope extends outward from the nucleus, creating a gaseous atmosphere that dwarfs anything previously observed. To comprehend this magnitude, consider that this coma stretches for roughly half the radius of our Sun, larger than most planetary orbits. No comet in the historical record has produced such an extensive carbon dioxide atmosphere, making Atlas a phenomenon without comparison. Traditional comet models predict coma formation through water ice sublimation as objects approach the sun's heating influence. Carbon dioxide typically plays a secondary role, present in smaller quantities and creating more modest atmospheric envelopes. Atlas appears to reverse this hierarchy, with CO2 dominating its outgassing to an unprecedented degree. This chemical composition challenges fundamental assumptions about how interstellar objects form and evolve. The sunward plume documented in Hubble and Gemini imagery violates basic physics as commonly understood in cometary science. Solar wind pressure should drive material away from the sun, creating the classic tail structure that defines these objects in popular imagination. Atlas displays exactly the opposite behavior, a prominent stream of material pointing directly toward our star, as if the object were defying fundamental forces that govern every other comet we've studied. This anti-tail phenomenon suggests dust grain characteristics unlike anything in our experience. Perhaps the particles are so massive that solar radiation pressure cannot overcome their inertia. Perhaps electromagnetic forces are interacting with charged particles in ways our models don't account for. Perhaps the object's rotation creates jets that launch material in directions that appear to contradict physical law. Each explanation requires assumptions that push beyond established cometary science. Reports of rapid brightening in mid-September added another layer to Atlas's anomalous behavior profile. Amateur astronomers tracking the object noted magnitude increases that exceeded theoretical predictions by significant factors. Some observers claimed brightening by 20 times the expected values, though these estimates remain unconfirmed through professional analysis. The discrepancies could reflect measurement errors, instrumental differences, or observational technique variations, rather than genuine anomalies. But what if the brightness reports prove accurate? A comet brightening 20 times faster than models predict suggests processes occurring within or around the nucleus that our understanding cannot accommodate. Perhaps sublimation rates are accelerating beyond normal thermal curves. Perhaps internal structure is exposing fresh, volatile materials to solar heating. Perhaps the object is undergoing fragmentation or structural changes that increase its effective surface area. The color transformation observed in late August and early September images adds visual drama to Atlas's growing list of unusual characteristics. Photographers began capturing a distinct green tint in the coma, likely caused by dicarbon or cyanide compounds excited by solar radiation. These chemicals commonly appear in comets, but their prominence in Atlas suggests either unusual abundance or enhanced excitation mechanisms. The tentative nature of the green coloration identification reveals another troubling aspect of the Atlas investigation. Visual observations and photographic evidence suggest chemical signatures that should be easily confirmable through spectroscopy. Yet definitive spectroscopic confirmation remains absent from public releases, despite multiple observatories having the capability to resolve these questions. Definitively, Atlas's trajectory through the inner solar system follows paths that seem almost choreographed for maximum observational opportunity. The close Mars encounter on October 3rd positions multiple orbiting spacecraft for unprecedented close-range observations. The perihelion passage in late October occurs at distances that should provide optimal conditions for studying cometary evolution under solar heating. The alignment with Earth's observation windows appears designed to maximize scientific return. This geometric convenience strikes some observers as more than coincidental, though orbital mechanics routinely produces surprising alignments through natural gravitational processes. The three-body interactions between Atlas, the Sun, and planets could naturally guide the object through trajectories that optimize viewing opportunities without requiring any artificial intervention or guidance. Public expectation management becomes critical when dealing with objects that behave as anomalously as Atlas. Citizens accustomed to regular space imagery releases naturally expect more documentation when objects become more interesting. The inverse relationship between Atlas's growing strangeness and decreasing public imagery creates cognitive dissonance that feeds conspiracy theories about deliberate concealment. Professional analysis pipelines slow down when confronted with data that doesn't fit established categories. Peer reviewers require more time to evaluate claims that challenge existing knowledge. Journal editors demand additional verification when papers describe unprecedented phenomena. The more extraordinary the observations, the longer the review process, and the greater the delay before public communication. The responsibility for explaining Atlas's characteristics falls heavily on institutions that may feel unprepared for the complexity involved. How do you communicate about an object that appears to violate multiple aspects of established cometry? Science? How do you maintain scientific credibility while acknowledging fundamental uncertainties about what you're observing? The challenge of public education around truly anomalous discoveries may exceed the communication capabilities that space agencies typically deploy. International coordination becomes more complex when dealing with observations that push scientific boundaries. Different institutions may reach different conclusions about the same data, creating potential conflicts that require diplomatic resolution before public release. The European Space Agency, NASA, and other organizations must balance their individual institutional interests with collaborative scientific goals while managing public expectations. The timing of Atlas's closest approaches unfortunately coincides with observational difficulties that compound communication challenges. Solar conjunction limits Earth-based observations, just as public interest peaks around the Mars flyby and perihelion passages. This temporal mismatch between optimal viewing conditions and maximum curiosity creates perfect conditions for speculation about what might be hidden during the observational blackout periods. Consider the implications if Atlas's anomalous characteristics prove to represent genuinely new physics, rather than unusual but explicable comet behavior. Discovery of phenomena that challenge fundamental assumptions about interstellar objects would require careful, methodical analysis before public announcement. The stakes for getting such announcements right might justify extended analysis periods that appear suspicious to outside observers. Yet the precedent set by Oumuamua and Borisov suggests that truly revolutionary discoveries benefit from transparent, real-time, scientific investigation rather than secretive analysis. The open debate around Oumuamua's non-gravitational acceleration ultimately strengthened rather than weakened public understanding of the discovery process. Atlas's more restrictive information flow represents a departure from this successful transparency model. The fundamental question becomes whether Atlas's silence reflects necessary scientific caution or institutional fear of public reaction to discoveries that might challenge established worldviews. Either explanation has profound implications for how extraordinary space discoveries will be communicated in the future, and whether the public will remain trusted partners in humanity's exploration of cosmic mysteries. Part 9. The Distraction Theory. September brought a curious shift in astronomical headlines that careful observers of space media couldn't help but notice. While Atlas approached its most scientifically interesting phase, the Mars flyby and subsequent perihelion passage, public attention was systematically redirected toward other celestial objects that offered more conventional, easily digestible cosmic entertainment. Comet Swan's dramatic fragmentation in early September provided exactly the kind of visual spectacle that space journalism craves. The object broke apart in real time, creating debris fields and evolving tail structures that amateur astronomers could photograph with backyard telescopes. NASA's astronomy picture of the day featured swan imagery multiple times, showcasing the photogenic destruction of a comet that behaved exactly as textbook physics predicted it should. The timing felt convenient for those seeking alternatives to Atlas coverage. Just as questions about the interstellar visitor's unusual behavior reached peak intensity, Swan offered a compelling distraction that required no complex explanations or uncomfortable acknowledgements of scientific uncertainty. Citizens could watch a comet die in predictable, comprehensible ways, rather than puzzle over anti-tails and unprecedented carbon dioxide comas. Comet Lemon emerged as another convenient focus for astronomical attention during September. Predictions suggested the object might reach magnitude 2 to 4 by late October, potentially becoming visible to naked-eye observers worldwide. Media outlets naturally gravitate toward phenomena their audiences can personally experience rather than telescopic mysteries that remain accessible only to specialists with sophisticated equipment. The promotion of Lemon's approaching visibility created a narrative of accessible astronomy that contrasted sharply with Atlas's technical complexity. citizens could step outside and potentially see Lemon with their own eyes, while Atlas remained an abstract concept supported only by difficult-to-interpret imagery from professional observatories. The psychological appeal of participatory astronomy versus passive consumption of expert analysis is obvious. Star Walk, Sky and Telescope, and other astronomical publications shifted their October comet coverage heavily toward Lemon's expected performance. Viewing guides, finder charts, and photography tips flooded online astronomy communities, creating a sense of anticipated excitement around an object that promised conventional cometary behavior. The implicit message suggested that citizens should focus on the comet they could see rather than worry about the one they couldn't understand. The perception among Atlas watchers was unmistakable. Attention was being deliberately redirected towards safer, more conventional celestial targets. Whether this represented conscious editorial coordination or natural media behavior toward accessible versus complex stories remained unclear, but the effect was identical regardless of intent. Public focus moved away from Atlas just as its most interesting characteristics were developing. Media psychology offers rational explanations for this coverage shift that don't require conspiracy theories. Journalists naturally prefer stories their audiences can engage with directly, rather than abstract scientific puzzles that require extensive technical explanation. Naked-eye comets generate more reader interest than telescopic objects because they create personal experience rather than vicarious learning through expert interpretation. The business model of astronomical journalism rewards accessibility over complexity. Articles about objects visible to amateur equipment generate more social media engagement, website traffic, and reader attention than pieces requiring sophisticated technical background to understand. Publishers responding to audience metrics would naturally emphasize Lemon over Atlas, regardless of any coordinated editorial agenda. Educational institutions face similar incentives when choosing which cosmic events to highlight in their public outreach programs. Planetarium shows, university lectures, and science museum exhibits benefit more from featuring phenomena that visitors can observe personally rather than abstract concepts that require faith in expert analysis. Atlas's complexity makes it poorly suited for general public education compared to conventional comets like Lemon. Yet the timing of this coverage shift feels suspiciously convenient for anyone seeking to minimize attention on Atlas's anomalous behavior. Just as the object's unprecedented characteristics were generating uncomfortable questions about gaps in scientific understanding, alternative targets emerged to absorb public curiosity about cometary phenomena in general. Professional astronomy conferences during September showed a similar pattern of emphasis. Presentations about Swan's fragmentation and Lemon's brightening outnumbered Atlas discussions, despite the interstellar visitor's far greater scientific significance. Whether this reflected genuine research priorities or strategic communication choices remained opaque to outside observers. Social media algorithms contributed to the attention shift in ways that might appear coordinated, but actually reflected automated engagement optimization. Posts about visible comets generated more shares, comments, and views than technical discussions about spectroscopic analysis or anti-tail physics. Platform algorithms naturally promoted content that produced higher user engagement, creating an artificial emphasis on accessible astronomy regardless of scientific importance. The European Space Agency's communication strategy during September focused heavily on other missions and discoveries rather than Atlas updates. Mars exploration achievements, Webb telescope revelations about distant galaxies, and Gaia spacecraft results dominated ESA press releases, while their Mars orbiters prepared for the most significant interstellar visitor encounter in human history. The contrast between preparation activities and public communication priorities seemed misaligned. Amateur astronomy communities showed interesting splits in their September discussions. While some forums maintained intense focus on Atlas tracking and imaging attempts, others shifted toward Lemon preparation and Swan documentation. The division might reflect different community priorities, scientific versus aesthetic interests, but it also dispersed the concentrated attention that Atlas had commanded during its peak visibility in August. The distraction theory gains credibility when viewed alongside historical precedents for managing public attention during sensitive discoveries. Government agencies routinely time potentially controversial announcements to coincide with other news events that might absorb media attention. While space agencies typically operate with greater transparency than other institutions, they face similar pressures to manage public reaction to discoveries that might cause confusion or concern. Whether deliberate distraction or natural media evolution, the September shift in astronomical coverage achieved the same result. Reduced public scrutiny of Atlas during its most scientifically critical phase. The object approached Mars, underwent perihelion heating, and potentially revealed its true nature while public. Attention focused elsewhere. The timing raises questions about whether this coverage pattern will continue through future encounters with equally anomalous interstellar visitors. Part 10. The Don't Look Up scenario. Netflix's 2021 film Don't Look Up crystallized a fear that had lurked in public consciousness for decades. What if those in power chose to hide cosmic truth rather than risk the social disruption that revelation might cause? The movie's premise, authorities downplaying a genuine asteroid threat to avoid economic and political chaos, resonates with anyone who's witnessed how institutions manage information during crises. While fiction, it provides a useful framework for examining how real cosmic discoveries might be handled when they challenge comfortable assumptions about our place in the universe. Apply this lens to Atlas as a thought experiment, not an accusation. The object poses no direct threat to Earth. NASA's trajectory calculations confirm closest approach in December at 1.8 astronomical units, well beyond any collision risk. But what if Atlas represented a different kind of threat? Not to our physical safety, but to our conceptual framework about what's possible in the cosmos. Consider the psychological impact if Atlas's characteristics prove to indicate artificial origin or technological enhancement. The anti-tail behavior pointing directly toward the Sun could suggest propulsion systems beyond our understanding. The unprecedented scale of its carbon dioxide coma might indicate controlled outgassing for navigational purposes. The precise trajectory that optimizes observation opportunities could reflect deliberate course corrections rather than natural orbital mechanics. None of these speculations represent confirmed observations. They're extrapolations from anomalous but potentially explicable phenomena. Yet if space agencies possessed evidence suggesting artificial characteristics, would immediate public disclosure serve the greater good? The social disruption from confirming that we're being visited by technology beyond our comprehension might justify temporary secrecy, while experts develop frameworks for productive public engagement. The historical precedent for managing revolutionary discoveries suggests that institutions default toward caution rather than transparency when faced with information that might fundamentally alter worldviews. The decades-long delay between military UAP encounters and public acknowledgement demonstrates how national security concerns can override scientific transparency when phenomena resist conventional explanation. Economic considerations add another dimension to potential disclosure calculations. Confirmation that interstellar visitors possess technologies we don't understand could destabilize markets, currencies, and entire industrial sectors. If Atlas demonstrated propulsion capabilities that made current transportation technologies obsolete, the economic implications might dwarf any scientific benefits of immediate public awareness. Religious and philosophical disruption could also influence decisions about disclosure, timing, and methods. Many worldviews depend on assumptions about humanity's uniqueness or centrality in cosmic affairs. Evidence that advanced civilizations routinely traverse the galaxy might require careful preparation of public opinion to prevent social fragmentation or existential crisis among populations unprepared for such revelations. The Don't Look Up scenario assumes that authorities possess definitive evidence of extraordinary phenomena, but choose concealment over transparency. In reality, the situation with Atlas more likely involves genuine uncertainty about how to interpret anomalous observations. Scientists may be struggling to distinguish between unknown natural processes and potentially artificial characteristics, making premature disclosure scientifically irresponsible regardless of harm. Political considerations. International coordination complicates any hypothetical concealment strategy. Multiple space agencies and research institutions are studying Atlas independently, making coordinated secrecy difficult to maintain without obvious evidence of suppression. The European Space Agency, NASA, Chinese space program, and other national organizations would need unprecedented cooperation to maintain consistent information management across different political and institutional cultures. Amateur astronomy presents another obstacle to systematic concealment. Backyard observers with increasingly sophisticated equipment can detect and analyze cosmic phenomena independently of official sources. The global network of amateur astronomers creates redundant observation capabilities that would make complete suppression of anomalous discoveries nearly impossible to sustain over extended periods. The Internet age has fundamentally altered information control dynamics compared to previous eras, when government or institutional gatekeepers could more easily manage public access to sensitive discoveries. Social media, online forums, and international communication networks create multiple channels for information sharing that bypass traditional authority structures. Yet the selective release of information remains possible, even in transparent societies. Timing announcements to minimize public attention, emphasizing conventional explanations while de-emphasizing anomalous characteristics, and focusing media coverage on alternative topics can shape public understanding without requiring outright deception. The question becomes whether we would recognize a "don't look up" scenario if we were experiencing one. The absence of dramatic announcements about Atlas's characteristics could reflect either routine scientific caution or deliberate information management designed to prevent social disruption. Distinguishing between these explanations requires access to internal, decision-making processes that remain opaque to outside observers. The film's ultimate message suggests that truth emerges, regardless of authority, to attempts at concealment, but often too late to serve the public good effectively. If Atlas represents a genuine paradigm shift in our understanding of interstellar visitors, delayed disclosure might sacrifice the opportunity for productive public engagement and democratic participation in humanity's response to extraordinary cosmic discoveries. The psychological power of the "don't look up" narrative lies in its recognition that authorities routinely prioritize stability over truth when facing information that might disrupt established order. Whether this dynamic is operating around Atlas remains speculative, but the pattern of reduced transparency during the object's most interesting phase certainly provides fertile ground for such concerns to flourish in public imagination. Part 11. Juno and the Blind Eye. The Internet's collective imagination seized on a tantalizing possibility during Atlas's rise to prominence. Why not redirect NASA's Juno spacecraft from its Jupiter orbit to intercept the interstellar visitor? The suggestion gained traction in online forums and social media discussions, appealing to our natural desire for close-up investigation of cosmic mysteries. Here was humanity's chance to get detailed imagery, chemical analysis, and definitive answers about Atlas's anomalous characteristics. The reality of spacecraft operations proved far more constraining than public enthusiasm anticipated. Juno currently orbits Jupiter in a highly elliptical path, designed to study the giant planet's atmospheric dynamics and interior structure. Retargeting the spacecraft toward an intercept trajectory with Atlas would require a massive velocity change, what aerospace engineers call a delta-V maneuver, that could demand more fuel than Juno carries. Technical assessments on platforms like Space Exploration Stack Exchange painted a sobering picture of the engineering challenges involved. The spacecraft would need to escape Jupiter's gravitational well, adjust its trajectory to match Atlas's path, and time the maneuver to achieve intercept near the comet's March 2026 Jupiter flyby. The required propulsive energy likely exceeds Juno's remaining fuel capacity, making the mission profile technically unfeasible with current resources. But the public discussion revealed something more interesting than spacecraft limitations: the assumption that NASA would naturally want to investigate Atlas up close if technically possible. Media pieces and opinion columns advocated for the Juno retargeting as an obvious choice, questioning why the space agency hadn't already announced such plans. The absence of official interest in close-up Atlas investigation began to feel suspicious to observers expecting aggressive scientific pursuit of anomalous discoveries. Harvard's Avi Loeb emerged as a prominent advocate for enhanced Atlas investigation, including spacecraft missions designed to study the object's characteristics in detail. His articles in publications like the Boston Herald argued that humanity was missing an unprecedented opportunity to examine an interstellar visitor that might hold keys to understanding planetary formation processes in other star systems, or potentially more exotic possibilities. The pushback from mission planning experts highlighted the conservative nature of space agency decision-making when faced with uncertain scientific returns. Spacecraft missions require years of planning, extensive technical review, and substantial financial commitment. Redirecting existing missions toward targets of opportunity involves risks that could compromise primary scientific objectives without guaranteeing compensating discoveries. Other spacecraft geometries offered less dramatic but potentially valuable observation opportunities that received minimal public discussion. NASA's Psyche mission, currently en route to study a metal-rich asteroid, might achieve distant observations of Atlas depending on trajectory timing. The European Space Agency's JWST spacecraft could potentially capture imagery during its journey toward Jupiter's moons. These opportunities lacked the drama of close intercept missions, but could still provide valuable scientific data. The Parker Solar Probe represented perhaps the most intriguing observation possibility, with its wide-field imager for Solar Probe, WISPR instrument, potentially capable of capturing Atlas during the comet's perihelion passage in late October and early November. The spacecraft's position near the Sun could provide unique perspective on Atlas's unusual anti-tail behavior and coma evolution during peak solar heating. Yet public discussion of these observation opportunities remained limited compared to the attention focused on more dramatic intercept scenarios. The emphasis on close-up investigation reflected popular misunderstanding of how astronomical discovery typically operates, through patient observation from multiple perspectives rather than single decisive encounters. The absence of announced spacecraft missions targeting Atlas prompted speculation about hidden policy decisions or classified reconnaissance capabilities. If the object displayed characteristics suggesting artificial origin, wouldn't military or intelligence agencies deploy space-based sensors for closer examination? The lack of visible response might indicate either absence of concerning discoveries or successful concealment of investigation activities. Commercial space capabilities add another dimension to potential Atlas investigation that received little attention in mainstream coverage. Private companies increasingly possess spacecraft and launch capabilities that could support rapid response missions to objects of interest. The absence of announced commercial initiatives might reflect economic calculations rather than lack of technical capability. International space agencies showed varying levels of public interest in Atlas observation opportunities. While the European Space Agency announced plans for Mars orbiter observations during the October flyby, other national space programs remained quiet about their Atlas investigation priorities. The uneven international response could reflect different scientific priorities or varying levels of concern about the object's anomalous characteristics. The Chinese space program's silence on Atlas investigation plans particularly intrigued observers familiar with their growing space exploration capabilities. China possesses spacecraft and launch technology capable of supporting interstellar visitor studies, yet public announcements about Atlas observation priorities remained absent from their typical communication channels. Amateur space organizations and university research programs represent untapped resources for Atlas investigation that received minimal consideration in mainstream coverage. Student-built CubeSats and privately funded space missions could potentially contribute valuable observations at lower cost than traditional government programs. Yet coordination with these communities appeared limited. The fundamental question underlying all spacecraft discussion became whether humanity was truly making maximum effort to investigate our third confirmed interstellar visitor, or whether institutional caution was preventing optimal scientific response to a potentially unprecedented discovery opportunity. The gap between public expectation of aggressive investigation and apparent institutional reluctance suggested either hidden constraints or deliberate policy choices that limited our cosmic curiosity. As Atlas approached its closest encounters with Mars and the Sun, the absence of dedicated spacecraft investigation began to feel like a missed opportunity of historical proportions. Whether this reflected reasonable resource allocation or more troubling institutional blindness to cosmic significance remained an open question that future interstellar visitor encounters might answer differently. Part 12. Mars Flyby. the moment of truth. October 3rd, 2025, represents humanity's best chance to capture definitive imagery of Atlas since the mysterious drought of telescope releases began in August. On this date, the interstellar visitor will pass within approximately 30 million kilometers of Mars, roughly 19 to 20 hundredths of an astronomical unit, positioning multiple orbiting spacecraft for unprecedented close-range observations of our enigmatic cosmic guest. The European Space Agency has confirmed their intention to attempt observations using Mars Express and the ExoMars Trace Gas Orbiter, two sophisticated spacecraft equipped with high-resolution imaging and spectroscopic capabilities. NASA's Mars Reconnaissance Orbiter, with its powerful high-rise camera system, could potentially join the observation campaign depending on orbital geometry during the flyby window. MAVEN, focused primarily on atmospheric studies, might contribute additional data about any interaction between Atlas's extensive coma and the Martian environment. What we might discover during this brief observational window could finally resolve the questions that have been building around Atlas since August. The morphology of that unprecedented carbon dioxide coma, extending outward for 348,000 kilometers, should become clearly visible to Mars-based instruments. The mysterious anti-tail behavior, pointing directly toward the Sun in defiance of conventional comet physics, might reveal structural details that explain its unusual characteristics. Spectroscopic analysis during the Mars encounter could confirm or refute the tentative chemistry suggested by Earth-based observations. Is the reported green coloration truly caused by dicarbon or cyanide compounds? Does the massive CO2 envelope really dominate the object's composition to the unprecedented degree that preliminary data suggests? These fundamental questions about Atlas's chemical nature might finally receive definitive answers. The resolution capabilities of Mars orbiters, while limited by the 30 million kilometer observing distance, could still provide scientifically valuable data about Atlas's nucleus size and surface characteristics. Harvard's Avi Loeb has suggested that even high-rise observations would resolve features of tens of kilometers per pixel at that range, sufficient to distinguish between conventional cometary nuclei and more exotic structural possibilities. But here's where the optimism about Mars observations encounters the same pattern of uncertainty that has characterized Atlas coverage since August. Will we actually see the results quickly, completely, and without editorial filtering? The history of space agency communication around Atlas suggests that even dramatic discoveries might undergo extended analysis periods before public release, potentially lasting weeks or months, while scientists interpret anomalous findings. Data latency represents a legitimate constraint on immediate release of Mars flyby observations. Even if spacecraft capture extraordinary imagery on October 3rd, the communication delays, data processing requirements, and scientific analysis pipelines will naturally introduce gaps between observation and public announcement. But how long should such delays reasonably last for images of obvious public interest? The critical question for anyone following this story becomes whether Mars flyby observations will receive the transparent, rapid release treatment that previous interstellar visitors enjoyed, or whether they'll disappear into the same analytical black hole that has characterized Atlas coverage for the past 2 months. The answer may determine whether public trust in space agency, transparency survives contact with genuine cosmic mysteries. Consider the psychological dynamics operating around this flyby window. After weeks of relative silence from major observatories, the Mars encounter represents a make-or-break moment for maintaining public engagement with Atlas's story. Successful, transparent sharing of flyby results could restore confidence in institutional scientific communication. Extended delays or selective release of findings could permanently damage public trust in how extraordinary discoveries are managed. The international cooperation aspect of Mars observations adds both opportunity and complexity to the situation. Multiple space agencies operating different spacecraft could produce complementary datasets that strengthen overall scientific understanding. But coordinating public releases across different institutional cultures and communication protocols naturally introduces delays that might appear suspicious to observers already primed to expect information management. Mars orbital mechanics during the flyby period will determine which instruments can achieve optimal viewing geometries for Atlas observations. The relative positions of spacecraft, Mars, and the comet must align favourably for high-quality imaging, spectroscopy, and other measurements. Not every orbiter will necessarily achieve useful observing conditions, potentially limiting the scope of data collection. The timing of Mars observations coincides unfortunately with Atlas's approach towards solar conjunction as seen from Earth. This means that even if Mars spacecraft capture definitive images, ground-based telescopes cannot provide immediate confirmation or complementary observations due to unfavourable solar angles. The temporary isolation of Mars-based data might contribute to delays in publication, while scientists await corroborating evidence from other sources. Weather and operational constraints could affect Mars observation quality in ways that won't become apparent until after the flyby. Window closes, dust storms, spacecraft maintenance requirements, or competing science priorities might compromise the planned observation campaigns. The gap between anticipated and achieved observational results could influence both the timeline and content of public releases about flyby findings. The European Space Agency's track record with Mars mission communications provides some basis for optimism about transparent flyby coverage. ESA has generally maintained open communication about Mars exploration discoveries, sharing imagery and scientific results with minimal delays. But Atlas represents an unprecedented case where the stakes for proper interpretation might justify more cautious communication approaches. NASA's approach to Mars flyby communication will likely reflect their overall institutional response to Atlas's anomalous characteristics. If they've been managing information carefully due to interpretive uncertainties, the Mars encounter might not change that approach even if spectacular results are obtained. Alternatively, definitive observations that clarify Atlas's nature might finally enable more open communication about its unusual properties. The countdown to October 3rd carries weight beyond mere scientific curiosity. This flyby represents a test of whether extraordinary cosmic discoveries can still receive transparent public treatment in an era of increasing institutional caution about information that might challenge established understanding. The eyes of citizen scientists, amateur astronomers, and concerned observers worldwide will be watching not just for what the Mars spacecraft discover, but for how quickly and completely those discoveries are shared with the humanity whose curiosity and support makes space exploration possible. Part 13. What happens at perihelion? October 29th to 30th marks Atlas's moment of maximum solar heating, when our interstellar visitor reaches perihelion at approximately 1.36 to 1.4 astronomical units from the Sun, just inside Mars's orbital distance. This represents the stress test that will either confirm Atlas as an unusually exotic but ultimately conventional comet, or reveal characteristics that fundamentally challenge our understanding of what interstellar objects can be. Physics operates with unforgiving precision during perihelion passages. Solar radiation intensity follows inverse square laws that concentrate enormous energy on any object approaching within the inner solar system. For comets, this heating drives sublimation of volatile compounds trapped within their nuclei, creating the spectacular outgassing events that generate visible comas and tails. Atlas has already demonstrated unprecedented behavior during its approach. What will happen when solar energy reaches maximum intensity? The massive carbon dioxide coma, already extending for 348,000 kilometers, could undergo dramatic evolution during peak heating. Traditional comet models predict that increased solar energy should drive faster sublimation rates, potentially expanding the coma even further, or altering its chemical composition as different, volatile compounds reach sublimation thresholds. But Atlas has already shattered traditional expectations, making predictions about its perihelion behavior largely speculative. Outburst events represent one possibility for perihelion drama that could provide definitive answers about Atlas's internal structure. Many comets experience sudden brightening episodes during close solar approaches, when internal pressure buildup causes explosive release of trapped volatiles. If Atlas undergoes such outbursts, the resulting debris patterns and chemical signatures could reveal whether its nucleus contains conventional comet materials or more exotic compositions. the mysterious anti-tail behavior, pointing directly toward the Sun in violation of standard physics expectations, might become more pronounced or undergo changes during perihelion heating. If this phenomenon results from unusual dust grain characteristics or electromagnetic interactions, increased solar energy could amplify these effects. Alternatively, conventional radiation pressure might finally overcome whatever forces create the sunward plume, causing Atlas to develop more typical tail structures. Fragmentation represents both an opportunity and a risk during Atlas's perihelion passage. The thermal and tidal stresses of close solar approach could cause the object to break apart, potentially revealing internal structure that has remained hidden within an intact nucleus. But fragmentation could also scatter the evidence we need to understand Atlas's true nature, creating multiple smaller objects with individual characteristics that complicate rather than clarify the overall picture. If Atlas survives perihelion intact, post-conjunction observations from Earth beginning in early December could provide the definitive chemical and morphological data that has been missing since August. By December, the object will have completed its closest solar approach and begun its outbound journey, potentially displaying evolved characteristics that reveal how solar heating affected its unusual properties. The wish list for perihelion observations includes confirmation of the CO, two dominants suggested by early SphereX observations, definitive spectroscopic identification of the compounds responsible for the reported green coloration, and high-resolution imaging of the nucleus that could constrain its size, shape, and rotational properties. These measurements could finally distinguish between natural processes and potentially artificial characteristics. Dust grain analysis during perihelion heating could explain the anti-tail mystery through detailed study of particle sizes, compositions, and charge states. If Atlas ejects dust with unusual electromagnetic properties, solar wind interactions during file, the perihelion might create observable effects that clarify the physics behind its counterintuitive tail behavior. The timing of perihelion heating coincides with solar conjunction conditions that limit Earth-based observations, creating a frustrating gap between the most scientifically interesting period and our ability to study it directly. This observational blackout means that perihelion changes might not become apparent until December, when Atlas emerges from the Sun's glare for post-conjunction study. International space agencies have made no public announcements about specialized perihelion observation campaigns, despite this representing Atlas's most critical evolutionary phase. The absence of coordinated observation efforts suggests either that agencies consider the object's behavior sufficiently understood to not warrant special attention, or that observation plans exist but aren't being shared publicly. The Parker Solar Probe's position near the Sun during late October and early November could provide unique observations of Atlas during or immediately after perihelion, but no official plans for such observations have been announced. This represents a missed opportunity for close solar observations that could reveal details invisible from Earth-based telescopes. Amateur astronomy communities are preparing for post-conjunction observations in December, but the months-long gap between perihelion and renewed visibility means that critical evolutionary processes will occur without public documentation. The scientific community will depend on whatever observations space-based assets might capture during the conjunction period, assuming such observations are planned and eventually shared. The psychological impact of the perihelion passage extends beyond scientific curiosity to questions about institutional transparency during critical observational windows. If Atlas undergoes dramatic changes during solar heating, but those changes aren't immediately shared with the public, the pattern of selective information release that has characterized its coverage could become irreversibly damaging to public trust in space agency communications. Climate and seasonal observation conditions in December will determine the quality of post-perihelion Atlas studies from Earth-based telescopes. Northern Hemisphere winter observing conditions, combined with Atlas's position relative to bright star fields, could limit the resolution and sensitivity of follow-up observations just when the object might be displaying its most evolved and informative characteristics. The fundamental question underlying perihelion expectations is whether Atlas will prove to be an exceptionally unusual but ultimately natural phenomenon, or whether its characteristics will evolve in ways that challenge basic assumptions about what's possible for objects originating in interstellar space. The answer to that question may determine how future interstellar visitors are studied, communicated about, and understood within the broader context of humanity's place in a cosmos that clearly holds surprises we're only beginning to appreciate. Part 14. Project Bluebeam and Government Secrets. Enter the realm of theoretical information warfare, where the line between legitimate scientific caution and deliberate manipulation becomes difficult to discern. Project Bluebeam, a conspiracy theory originating in the 1990s, postulates that governments might stage false cosmic events using advanced technology to manipulate public opinion and establish new forms of social control. While lacking credible evidence, this theory provides a framework for examining how genuine cosmic discoveries might be managed when they challenge established power structures or social stability. The theory suggests that holographic projections, satellite-based displays, and coordinated media manipulation could create artificial astronomical events designed to unite populations under new belief systems or governmental authorities. Applied to Atlas, this framework raises speculative questions about whether its unusual characteristics might serve psychological operations rather than representing genuine anomalous phenomena. Consider the timing of Atlas's discovery and subsequent media coverage within broader patterns of social manipulation that characterize modern information warfare. The object appeared during a period of global uncertainty, offering a cosmic mystery that could redirect public attention from terrestrial concerns toward existential questions about humanity's place in the universe. Whether by coincidence or design, Atlas has provided distraction from political, economic, and environmental crises that might otherwise demand more focused public attention. The gradual release of increasingly extraordinary claims about Atlas, from unusual composition to unprecedented coma scale to anti-tail behavior, follows psychological conditioning patterns designed to gradually expand public acceptance of anomalous phenomena. Rather than immediate revelation of the object's most unusual characteristics, information has been parceled out in doses that allow public opinion to gradually accommodate increasingly strange possibilities. But Project Bluebeam speculation requires capabilities that exceed demonstrated technological reality. Creating convincing holographic displays visible through professional telescopes worldwide would require coordination and technology that no known government possesses. The theory assumes central control over decentralized observation networks that operate independently across multiple national boundaries and institutional cultures. The international nature of Atlas observations presents the strongest counterargument to Project Bluebeam scenarios. European, American, Chinese, and other national space programs have independently confirmed the object's existence and characteristics using separate instrument systems and analysis protocols. Coordinating deception across these diverse institutional and political contexts would require unprecedented cooperation that extends far beyond historical precedent for international coordination in any field. Amateur astronomy provides another verification layer that complicates any hypothetical deception scenario. Thousands of independent observers using personal equipment have captured Atlas imagery and confirmed its unusual characteristics through their own analysis. This distributed observation network operates outside government control and would be extremely difficult to manipulate without obvious evidence of coordinated interference. Yet selective emphasis and interpretation of genuine observations could achieve manipulative effects without requiring false phenomena. If Atlas displays genuinely anomalous characteristics, authorities could choose to emphasize certain aspects while downplaying others, guiding public interpretation toward desired conclusions without creating false evidence. The line between scientific caution and narrative manipulation might be invisible to outside observers. The UAP disclosure process provides a real-world template for how extraordinary phenomena receive gradual acknowledgement rather than immediate transparency. Military encounters with unexplained aerial objects remained classified for decades before recent partial disclosures that acknowledge the reality of anomalous phenomena while carefully managing public interpretation of their flown significance. This precedent suggests that genuine cosmic anomalies might receive similar treatment, acknowledgement, without complete revelation. Modern information warfare operates through narrative control rather than fabricated events. Rather than creating false astronomical phenomena, sophisticated manipulation might focus on shaping how genuine discoveries are interpreted and understood by public audiences. The framing of Atlas as either a conventional, if unusual, comet, or potentially artificial visitor could be guided through selective release of information that supports desired interpretations. The psychological impact of cosmic discoveries on religious and philosophical worldviews creates legitimate concerns about disclosure, timing, and methodology that don't require conspiracy theories to explain. Evidence suggesting that advanced civilizations regularly traverse the galaxy might require careful preparation of public opinion to prevent social fragmentation or existential crisis among populations unprepared for such revelations. Economic disruption represents another rational concern that could influence disclosure decisions without requiring nefarious motives. Confirmation that interstellar visitors possess technologies beyond human understanding could destabilize markets, currencies, and entire industrial sectors. Gradual preparation of economic systems for paradigm-shifting revelations might justify temporary information management during analysis periods. National security considerations add complexity to disclosure calculations that extend beyond simple concealment motives. If Atlas demonstrates capabilities that could be weaponized or that reveal vulnerabilities in human space defense systems, careful analysis of strategic implications might take precedence over immediate public satisfaction of curiosity about anomalous characteristics. The Internet age has fundamentally altered information control dynamics compared to previous eras when centralized authorities could more easily manage public access to sensitive discoveries. Social media, international communication networks, and distributed observation capabilities create multiple channels for information sharing that make complete suppression of extraordinary discoveries increasingly difficult to maintain. Yet, sophisticated influence operations can shape public interpretation of genuine phenomena without requiring false flag operations or fabricated evidence. The emphasis placed on conventional explanations for Atlas's unusual characteristics, the timing of alternative comet coverage during peak interest periods, and the selective release of observational data could guide public understanding toward desired conclusions through subtle manipulation rather than outright deception. The fundamental challenge in evaluating Project Bluebeam scenarios lies in distinguishing between reasonable scientific caution and potentially manipulative information management. Both approaches might produce identical observable patterns, delayed releases, selective emphasis, coordinated institutional messaging, making outside verification of motives nearly impossible without access to internal decision-making processes. Media literacy becomes crucial for citizens attempting to navigate the complex information environment surrounding extraordinary cosmic discoveries. Understanding how institutional incentives, economic pressures, and political considerations influence scientific communication helps distinguish between legitimate analytical caution and potentially manipulative narrative control. The danger of Project Bluebeam thinking lies not in its specific claims about holographic technology, but in its recognition that information can be weaponized to serve interests beyond pure scientific understanding. Whether Atlas represents genuine anomalous phenomena or carefully managed conventional discovery, the pattern of its public presentation reflects institutional priorities that may not align with public interests in complete transparency. As we approach the Mars flyby and subsequent perihelion passage, the crucial question becomes whether Atlas observations will receive treatment that prioritizes scientific transparency over other considerations. The answer may determine not only what we learn about this particular interstellar visitor, but how future cosmic discoveries are managed within the complex intersection of science, politics, and public understanding. Part 15. How space images actually become public. Behind every stunning space image that graces NASA's website or floods social media feeds lies a complex journey, from cosmic photons to polished press release. Understanding this pipeline reveals why the silence around Atlas might reflect mundane technical realities rather than sinister concealment, though the distinction often becomes invisible to outside observers hungry for immediate cosmic gratification. The process begins long before any telescope points toward a target. Observing time on flagship instruments like Hubble and the James Webb Space Telescope gets allocated months or even years in advance through competitive peer review processes. Scientists submit detailed proposals explaining why their targets deserve precious telescope hours, competing against hundreds of other research programs for limited observational windows. Target of opportunity requests exist for truly extraordinary events that couldn't be predicted during the regular proposal cycles. Supernovas, asteroid impacts, or unusual comet behavior can trigger emergency observations that interrupt carefully planned observing sequences. But the threshold for such interruptions is high, requiring compelling scientific justification that extends beyond mere public curiosity about anomalous phenomena. Even when data collection occurs, press teams must decide whether observations warrant public release. Not every astronomical measurement produces visually striking imagery suitable for general audiences. Spectroscopic data, photometric measurements, and technical calibration frames might contain scientifically valuable information while lacking the visual appeal necessary for effective public communication. Raw telescope data requires extensive processing before it becomes suitable for analysis, let alone public display. Bias frames must be subtracted to remove instrumental noise. Dark current exposures eliminate thermal artifacts from detector systems. Flat field corrections account for variations in pixel sensitivity across camera arrays. These calibration steps operate automatically, but require time and computational resources. Image co-registration aligns multiple exposures to compensate for telescope tracking variations and atmospheric turbulence. Cosmic ray removal algorithms identify and eliminate energetic particle strikes that create false features in astronomical images. Multiple exposures must be combined using sophisticated statistics that maximize signal while minimizing noise artifacts. Context becomes crucial before any processed image reaches public channels. Scientists need temporal baselines to understand whether observed features represent permanent characteristics or transient phenomena. Spectroscopic analysis provides chemical context for interpreting morphological structures. Geometric calculations determine viewing angles and solar illumination conditions that affect feature visibility. The analysis timeline extends further when observations reveal unexpected characteristics. Standard processing workflows assume conventional astronomical targets with predictable behavior patterns. Anomalous objects like Atlas require custom analysis approaches that can add weeks or months to the publication timeline, as scientists develop new methods for interpreting unprecedented phenomena. Mission teams often wait for minimal analysis completion before releasing representative images to avoid public misunderstanding of preliminary results. Basic photometric measurements confirm brightness levels and temporal evolution. Spectroscopic analysis identifies dominant chemical constituents. Instrument health checks verify that unusual features reflect genuine astronomical phenomena rather than equipment malfunctions or calibration errors. Geometry constraints add another layer of complexity during certain observational periods. Solar conjunction creates pointing restrictions designed to protect sensitive instruments from solar radiation damage. Even space-based telescopes maintain strict limits on angular separations from the Sun to prevent catastrophic overheating of detector systems and optical components. Earth-based observations face additional constraints from atmospheric absorption, weather patterns, and seasonal visibility windows. Objects approaching solar conjunction become increasingly difficult to observe from ground-based facilities, creating natural gaps in coverage that have nothing to do with institutional secrecy or information management policies. Data rights and embargo periods create legitimate delays in image release that reflect scientific publication practices rather than concealment motives. Some missions maintain proprietary periods that allow discovery teams exclusive access to their data for limited timeframes. These policies protect the investment of scientists who proposed and planned observations while ensuring that scientific analysis precedes popular media coverage. Internal caution influences release timing when observations reveal morphological characteristics that resist straightforward interpretation. The sunward plume behavior, documented in Atlas imagery, requires careful explanation to avoid public misunderstanding about apparent violations of physical law. Communications teams naturally slow down to craft accurate explanations that convey scientific uncertainty without generating unwarranted alarm or speculation. Agency coordination becomes necessary when multiple observatories study the same target using different instruments and analysis approaches. Hubble, Webb, Gemini, and European Space Agency assets might observe Atlas independently, requiring coordination of public releases to maintain consistent messaging and appropriate attribution of discoveries across different institutional boundaries. The definition of new imagery creates confusion when processed observations appear weeks or months after initial data collection. Press offices may release images based on observations taken during optimal viewing conditions, but processed during periods when the target has become unobservable. To outside observers, this creates false impressions of observational gaps when teams are actually working continuously behind the scenes. Public memory of previous interstellar visitors contributes to unrealistic expectations about image release frequency. Oumuamua and Borisov benefited from simpler morphology and better observing geometry that enabled more rapid analysis and publication cycles. Atlas's complex behavior and challenging observation windows naturally require different communication approaches that feel restrictive by comparison. Professional astronomy has learned important lessons about managing public expectations during investigation of anomalous phenomena. The balance between sharing exciting discoveries promptly and avoiding premature conclusions requires careful navigation of communication strategies that prioritize accuracy over speed. Weather and operational constraints affect ground-based observations in ways that create unpredictable gaps in coverage. Dust storms, equipment maintenance, and competing observational priorities can interrupt planned observation campaigns. Cloud cover, atmospheric turbulence, and seasonal visibility changes introduce additional variables that influence data quality and availability. International collaboration adds complexity to communication timelines when multiple space agencies must coordinate their individual institutional interests with shared scientific goals. European, American, and other national space programs operate under different administrative and communication protocols that naturally introduce delays compared to single-source announcements. The technological infrastructure supporting modern astronomy creates dependencies that can affect release timing in ways invisible to outside observers. Data, storage systems, network connectivity, and computational resources all influence how quickly observations can be processed and analyzed. Bottlenecks in any part of the pipeline can delay public releases regardless of scientific readiness. Understanding these technical realities provides context for interpreting the silence around Atlas that extends beyond conspiracy theories or deliberate concealment scenarios. The complexity of modern astronomical observation and analysis naturally creates delays that feel suspicious to observers, expecting immediate gratification, but actually reflect the careful, methodical approach that produces reliable scientific results. The challenge for both scientists and the public lies in distinguishing between legitimate technical delays and potentially problematic information management when extraordinary discoveries challenge established understanding. Transparency about process limitations could help manage expectations while maintaining public trust in institutional commitment to sharing cosmic discoveries appropriately. Part 16. What to look for in the next images. When the next batch of Atlas imagery finally emerges, whether from Mars orbiters during the October 3rd flyby or post-conjunction Earth observations in December, having a systematic approach to evaluation will help distinguish genuine scientific discoveries from media hype, processing artifacts, and wishful thinking. The astronomical community has developed methods for separating signal from noise that any citizen scientist can apply to cosmic mystery investigation. The sunward plume phenomenon represents the most visually obvious target for analysis in any new Atlas imagery. Look for persistence of the anti-tail structure, pointing directly toward the sun, noting whether it appears as a narrow jet-like feature or a broader fan-shaped distribution of material. Changes in plume characteristics between observation epochs could indicate evolving dust grain, properties, rotational effects, or viewing geometry variations that provide natural explanations for this counterintuitive behavior. If the sunward plume weakens, disappears, or reverses direction in new images, such changes would suggest that conventional solar radiation pressure is finally overcoming whatever forces initially created the anomalous tail structure. This evolution would support natural rather than artificial explanations for Atlas's unusual morphology, while providing valuable insights into the physical processes operating within its coma environment. Fragmentation signatures offer another crucial diagnostic for interpreting Atlas's current state and future evolution. Multiple condensations near the nucleus, knot-like structures within the coma, or string of pearls, arrangements of discrete objects would indicate that thermal or tidal stresses are causing structural breakdown. Fragmentation occurs commonly in comets approaching perihelion and doesn't necessarily indicate artificial construction or exotic composition. However, fragmentation patterns that display geometric regularity, symmetrical arrangements, or non-random distributions might suggest internal structure more complex than typical cometary nuclei. The distinction between chaotic natural breakup and organized structural failure requires careful analysis, but could provide crucial evidence about Atlas's true nature. Brightness behavior analysis requires comparison between observed apparent magnitudes and theoretical light curve predictions based on standard cometary models. Steady brightening that follows inverse square law relationships with solar distance suggests conventional thermal response to increasing solar heating. Sudden spikes, followed by gradual fading, typically indicate outburst events caused by internal pressure buildup and explosive volatile release. Claims about 20-fold or greater brightness increases should be treated as preliminary estimates requiring confirmation through systematic photometry using calibrated instruments. Amateur observations provide valuable temporal coverage, but often lack the precision necessary for definitive brightness analysis without professional verification and standardization. Color analysis presents both opportunities and pitfalls for interpreting Atlas imagery. Green hues visible in processed images could indicate dicarbon or cyanogen emission from solar-excited molecules, but color assignments in astronomical imagery often reflect artistic choices rather than direct spectroscopic measurements. Without accompanying spectral data, color information remains suggestive rather than definitively diagnostic of chemical composition. Filter selection and processing techniques can dramatically affect the apparent colors visible in astronomical images. Different wavelength bands emphasize different physical processes and chemical constituents, making direct color interpretation potentially misleading without understanding the technical details of image acquisition and processing methods. Spectroscopic information, when available, provides the most reliable chemical analysis of Atlas's composition and behavior. Look for specific mentions of carbon dioxide, cyanogen, water vapor, and dicarbon in official releases, noting the relative abundances and how they compare to typical cometary chemistry. Dominance of CO2 over water vapor would confirm the unprecedented compositional characteristics suggested by earlier observations. Tail architecture examination should focus on the alignment and structure of both dust and ion tail components. Primary dust tails should extend anti-sunward under pressure from solar radiation, while narrower ion tails follow magnetic field lines and solar wind flow patterns. Multiple tail structures at different angles can appear during outburst events, or when viewing geometry changes reveal previously hidden features. Nucleus size estimates provide constraints on Atlas's physical dimensions even when individual resolution remains insufficient to resolve surface details. Professional analysis can infer nuclear dimensions through coma modeling and light curve analysis, but beware of media claims providing exact measurements based on fuzzy photographic evidence without accompanying uncertainty estimates. Non-gravitational acceleration detection requires precise astrometric measurements over extended time periods to distinguish rocket-like forces from gravitational perturbations. Single images cannot demonstrate such effects, but consistent position measurements that deviate from pure gravitational predictions would indicate gas, jet, or other propulsive forces acting on the object. Mars orbiter observations offer geometric advantages through different viewing angles and reduced atmospheric interference, but distance limitations still constrain resolution and detail visibility. Expect modest image quality improvements rather than dramatic close-up revelations that exceed the fundamental physics of observation at 30 million kilometer distances. Cross-validation between independent observation systems provides the strongest evidence for genuine phenomena versus instrumental artifacts or processing errors. Features that appear consistently in data from Mars orbiters, ground-based telescopes, and space-based instruments gain credibility that single-source claims cannot achieve. Image authenticity verification becomes crucial when extraordinary claims accompany unusual imagery. Over-sharpened edges, impossibly detailed surface features, or star field inconsistencies might indicate excessive processing or deliberate falsification. Trust established mission archives and peer-reviewed publications over sensational social media claims lacking institutional verification. Following reliable information sources helps navigate the complex landscape of astronomical discovery reporting. Official mission blogs, professional astronomy society circulars, and established amateur-professional collaboration networks provide more credible information than speculative websites or social media accounts lacking scientific credentials. Prepare for potential disappointment when genuine scientific imagery often appears less dramatic than public expectations suggest. Real astronomical discovery frequently looks messy, ambiguous, or inconclusive compared to the clean narratives preferred by popular media. Individual observations gain meaning through combination with broader datasets rather than standalone dramatic revelation. If future Atlas imagery proves genuinely shocking, maintain systematic evaluation that considers natural explanations before entertaining more exotic possibilities. Unusual plasma physics, complex geometry effects, and fragmentation processes can create visually striking phenomena that challenge intuitive understanding without requiring artificial intervention or technological artifacts. The systematic approach to image analysis serves dual purposes, maximizing scientific understanding while maintaining healthy skepticism about extraordinary claims. Whether Atlas ultimately proves conventional or revolutionary, careful evaluation methods will help distinguish authentic cosmic discoveries from the inevitable mixture of wishful thinking, processing artifacts, and deliberate misinformation that accompanies any sufficiently mysterious astronomical phenomenon. This checklist provides tools for citizen participation in the scientific process of discovery, while maintaining the critical thinking skills necessary to navigate an information environment where genuine cosmic mysteries compete with speculation, hype, and deliberate deception for public attention and credibility. Part 17. Closing speculation, what we might be missing. Let's inventory what we know with uncomfortable precision. The timeline of official releases tells a story that should disturb anyone who values transparency in scientific 5. Discovery. Hubble's final public image of Atlas was captured on July 21st, released to the world on August 7th. The James Webb Space Telescope observed the object on August 6th, producing spectroscopic data that remains under analysis months later. Gemini South captured imagery on August 27th that wasn't shared until early September. Since then, virtual silence from the flagship telescopes that should be documenting this historic interstellar visitor. The European Space Agency has confirmed plans for Mars orbiter observations during the October 3rd flyby, representing our best hope for breaking the observational drought that has characterized Atlas coverage since late summer. But will those observations receive the transparent treatment that the public deserves, or will they disappear into the same analytical black hole that has swallowed the Webb spectroscopy results? Perihelion approaches on October 29th to 30th, when Atlas will endure maximum solar heating at approximately 1.4 astronomical units from the Sun. If the object survives this thermal stress test, it should re-emerge for Earth observations in early December, potentially displaying evolved characteristics that could finally answer the questions that have been building since July. The carbon dioxide coma remains the most extraordinary confirmed characteristic. 348,000 kilometers of CO2 envelope, extending outward from the nucleus, creating an atmosphere larger than most planetary orbits. No comet in recorded history has produced such an extensive carbon dioxide atmosphere, making Atlas a phenomenon without precedent or comparison. The morphological anomaly of the sunward plume continues to defy conventional physics as we understand it. Solar wind pressure should drive material away from the Sun, yet Atlas displays exactly the opposite behavior, a prominent anti-tail pointing directly toward our star, as if defying the fundamental forces that govern every other comet we've studied. Now comes the speculative inventory, clearly labelled as such. of what those missing images and delayed analyses might reveal if they were shared without institutional filtering. These scenarios remain hypothetical, but they represent the kinds of discoveries that could justify the careful information management we've been witnessing. Consider the possibility that recent imagery shows dust and gas patterns around Atlas that appear artificially structured rather than following the chaotic dynamics typically associated with cometary outgassing. Geometric arrangements of debris, symmetrical jet patterns, or organized material flows might suggest technological intervention rather than natural processes. Such characteristics would challenge fundamental assumptions about interstellar objects while raising uncomfortable questions about their origins and purposes. Fragmentation into non-random patterns could provide another explanation for extended analytical delays. If Atlas has begun breaking apart during its solar approach, the resulting debris field might display geometric characteristics that resist conventional interpretation. Hollow internal structures, regular fragment arrangements, or debris patterns that suggest manufactured components could require extensive analysis before public release. The spectroscopic mystery deepens when we consider what James Webb might have discovered in those August 6th observations that remain unreported. The chemical signature of Atlas's massive CO2 envelope should be straightforward to analyze and confirm, yet no definitive results have been shared. Perhaps the spectral lines reveal isotopic ratios that don't match solar system materials, suggesting formation conditions unlike anything in our local stellar environment. The reported green coloration could conceal more complex chemistry than simple dicarbon or cyanide excitation. If spectroscopic analysis reveals synthetic compounds or isotopic signatures that suggest industrial rather than natural processes, the implications would extend far beyond conventional comet science into questions about technological artifacts masquerading as natural phenomena. The anti-tail behavior might result from electromagnetic properties that indicate artificial propulsion systems rather than unusual dust grain characteristics. If Atlas is using controlled electromagnetic fields to manipulate material flows, creating the illusion of defying solar wind pressure, such capabilities would suggest technology far beyond human understanding. Even the trajectory itself raises questions when examined closely. The precise alignment with observational opportunities, close Mars encounter, optimal perihelion distance, favorable Earth viewing windows could reflect course corrections rather than natural orbital mechanics. Objects don't typically arrive with such convenient geometries for scientific study unless someone or something has planned those approaches. But ground ourselves in NASA's own documentation, which provides non-sinister explanations for the observational gaps we've been experiencing. Solar conjunction creates legitimate viewing difficulties that justify reduced Earth-based observations during Atlas's most interesting phase. Telescope scheduling constraints, analysis pipeline delays, and peer review requirements naturally extend the timeline between observation and public release for complex discoveries. The silence around Atlas could reflect nothing more than scientific caution when confronted with phenomena that challenge existing models. Professional astronomers prefer to understand anomalies thoroughly before making public claims that might later require embarrassing corrections. The complexity of interpreting Atlas's unusual characteristics might justify extended analysis periods that appear suspicious, but actually represent responsible scientific practice. International coordination requirements add legitimate delays when multiple institutions must align their findings before joint announcements. The European Space Agency, NASA, and other organizations naturally require time to coordinate public releases that maintain consistency across different national and institutional communication protocols. Yet the historical precedent of Oumuamua and Borisov suggests that genuine scientific discovery benefits from transparent, real-time investigation rather than secretive analysis. The open debate around previous interstellar visitors strengthened, rather than weakened, the public understanding of the discovery process, while Atlas's more restrictive information flow represents a troubling departure from this successful transparency model. The ultimate question becomes whether we're witnessing necessary scientific caution or institutional fear of public reaction to discoveries that might fundamentally alter our understanding of what's possible in the cosmos. Either explanation has profound implications for how extraordinary space discoveries will be communicated in the future, and whether the public will remain trusted partners in humanity's exploration of cosmic mysteries. In days, Mars orbiters may capture the close-range imagery that could either confirm Atlas as an exotic but ultimately conventional comet, or reveal characteristics that challenge everything we thought we knew about interstellar visitors. When those pictures finally arrive, and assuming they're shared with appropriate transparency, we may discover that we've been looking at interstellar visitors all wrong. The cosmos holds secrets that we're only beginning to glimpse, and Atlas may represent just the first of many discoveries that will force us to expand our understanding of what's possible in the dark spaces between stars. Whether we're ready for such revelations, and whether our institutions will trust us with the truth about what's really out there, remains the most terrifying question of all.